So in this talk, I will tell you about an idea that I put forward 1.5 years ago, which is the idea of fake particle, fakeon, which I think leads to the right theory of quantum gravity and solves the problems that you've heard about today and yesterday, and maybe you will hear about them also in the next days. I will also give you the physical implications and some predictions. I cannot cover the work that I've done in papers in the last 1.5 years because I only have 30 minutes. I will focus on the classical limit because in the classical limit we will see many features of the physical implications, in particular violation of micro-causality, and we will see in a concrete example the solution Friedman-Robinson work. What about scale invariance? This conference is about scale invariance. Wait till the last slide where I will give some maybe upsetting comments, messages. So the basic thing here is unitarity. Unitarity is the property that you see here, the property of the S matrix, which can be also written in this form for the T matrix, and it's known as optical theorem. Now, normally in higher derivative theories, you cannot prove that equation, but if you use the states from your Fock space, you will see that it contains some physical states, because instead of having the imaginary part equal to a sum of T dagger T with the completeness relation in between that should read like that, okay, you have some pluses, some minuses, some zeros. Zeros are not that worrying, but the minuses are ghosts. The optical theorem can be translated into cutting equations. It has a diagrammatic version. It is very nice. I give only the two basic examples, and for all other theorems I will have to send you to my papers. But just let me consider a three-level example and a one loop. Why is it this important? Remember that this is a quadratic equation. Since it is quadratic, it mixes different orders of the loop expansion. That's very crucial. So for example, if you take this vertex, the imaginary part is equal to something positive, because you see T dagger T tells you about some positivity. And if you go to the loop, one loop order, you get the imaginary part of the bubble diagram is similar, something positive, with the vertex that has been turned around. So here you have three level, one loop, three level. One loop speaks to three level, and we will see that this will affect enormously the classical limit. Now the propagator is this one. We will always, my procedure is I start from particle physics, even if it is quantum gravity. So I expand around flat space, and that is what I can deal with. This object needs a prescription, and normally what you do is to use the Feynman prescription, G+, I call it. Is it good? Of course it is good, because it satisfies the optical theorem. You can put it inside here. This is the propagator. It will be equal to some cut diagrams, but it's on the right hand side you find something positive. Here it is, the imaginary part of this distribution is positive. What is a ghost? A ghost is the same object with a minus sign in front. If you have a minus sign in front, you will have a minus sign there, and you will violate unitarity. Now, first message I want to tell you is that this is not only due to the sign in front. This is due to the sign in front, but also to this sign here. It is due to the prescription. If I change both, it's okay. If I flip the sign of the prescription and the sign that was in front, it's okay. So I have two possibilities, which I call G plus and G minus, plus, plus, minus, minus. Why don't we use them in quantum field theory? There is a reason why they cannot coexist. You can check a paper that I wrote with Alietti, a physicist from Rome. if you quantize these kind of theories where both propagators appear in Minkowski space, you will find so bad divergences, non-local divergences from a local theory, that really I don't know how to cure them, and I think that those theories are just inconsistent. What do you do then? There is only one way to make these two propagators coexist, and that's the idea of fake particle, the fakeon. Basically, let me start again from the propagator. It has two poles on the real axis. No prescription, but normally you would turn around them like this. Now, write a plus or minus sign in front just to show you that what I'm talking about works with a plus in front and with a minus. It doesn't really make a difference. Multiply by p squared minus m squared. Ignore the numerator for a moment. So doing, you split the poles into pairs. But if you keep that integration path, you have this integration. It's not Minkowski. It's Euclidean Wick rotated. And this integration path I call Lie-Wick integration path because it first appeared in the Lie-Wick models, although I will show you again that, in a moment that the Lie-Wick models were not formulated completely. So be aware of that whenever you talk about Lie-Wick models. To make things explicitly, let me introduce an infinitesimal width, epsilon here, so that you have a numerator, forget about it, and you have a denominator. The denominator will give you these four poles, here, 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 here. Fine. This is a superposition of the two operators that are admissible. But notice that, naively speaking, this is not an argument, this is not a proof, just a naive thing. If you evaluate this on shell, you get 0. So the idea is that you have no particle. What happens about the bad divergences that I mentioned before? They occur in Minkowski space. Do not take this on Minkowski space. If you did that, this distribution would be the principal value. The principal value is never used because it's bad. But the principal value is what you obtain if you integrate here. This is a totally different thing because it comes from the Euclidean and you integrate there, so it is not the input. Indeed, what you see here is not the end of the story. It's just a formal warm-up, because now I have to tell you how to make calculations and you will see what comes into the game. Let me do it in the simplest diagram, which is a bubble diagram with these two propagators. You integrate the loop energy on this fanicon 2, the Lie-Wick path. You integrate the space momentum where, well, you don't know, R3. That's what Lie and Wick suggested. That's wrong. That's the delicate part. What do you do? Let's do the first integral. You compute the residues. You will remain with the integral on the loop space momentum of a certain integrand. Okay? Then the result is an analytic function whenever this integrand is regular. Whenever this integrand is singular, you will have violations of analyticity. Normally they are branch cuts. Here they are not branch cuts. You have to study them in detail. This is the locus of the singularities. The external energy is equal to a sum of frequencies that are the frequencies of the two virtual particles, as usual, with the caveat now you have complex masses. But otherwise, this is the same formula as usual. If you plot this locus, geometric locus here, for k varying spanning R3, you get two surfaces filled entirely. These are surfaces of singularity. So the singularities are not just at the boundary, they are everywhere. Okay? So what do you do? If you these problems, by the way, were known soon after Lie and Wick, and somebody proposed, Katkowski and others, some prescription to solve them, but they admitted that those didn't remove the problem completely, and there were ambiguities. What you find is that if you want to compute your amplitude for some value of the external energy, that is, for example, here, the real value but here, the result of this calculation will be not Lorentz invariant and not analytic. Not analytic because there is a singularity, not Lorentz invariant is obvious. Once you have a funny way to integrate on the loop energy, you have to find a funny way, companion way to integrate on the loop space momentum. Otherwise, there is no hope to have Lorentz invariance. I claim I found that. There exists in this deformation, and in the papers you can even find it explicitly in the case of the bubble diagram. It's very nice, actually. Instead of integrating on a domain like this, you just deform it like that. Very, very simple. You have to complexify the loop space momentum as well. And you will find that there is a deformation of this domain where the entire surface shrinks into a half line from a threshold onwards, as you would like. Now what you have to do, this is the prescription. Again, as I said, the prescription is not just the formula I wrote before, because it's very, very delicate, but in the end it is rather simple. You want to compute some amplitude for some momentum that is like that, in this area. You compute it with the wrong domain, then you view it as a function of the domain, you deform the domain, and take the limit when that takes this area to a half line. When you take that limit, Lorentz invariance and analyticity are recovered. So basically it's like having, normally instead of having branch cuts, you have extended regions, you go inside them, and then you take the limit, epsilon going to 0. You are calculating inside the branch cuts. That's the solution. You have therefore an analytic function there inside. I'm not saying you have to compute the amplitude from above or from below. Those are the Feynman prescription and the conjugate of the Feynman prescription. You have to compute it inside. And now I told you how to do that. By analytic continuation, it is better to extend this, the analytic function you find on the cut, to a cone, because that's more explicit. So now you have the picture. You have what I call region-wise analyticity. In the Euclidean region, you will have an analytic function, whatever it is. Here, above the threshold, you will have another analytic function. The relation between this analytic function and this analytic function is not analytic, but it is unambiguous. Once you know the function in the Euclidean region, you know unambiguously the other analytic function in the above the threshold, and the same for all thresholds. Said differently, if you want to formulate your theory in Euclidean, that's the only option you have, and Vic rotated, you will find that the Vic rotation is not analytic. And you have to deal with that and give a prescription to make the Vic rotation correctly. But this prescription works and actually solves the problem of unitarity, because you see it's completely symmetric with respect to reflections with respect to the real axis. That means there is no imaginary part here, there is no imaginary part here, and there is no imaginary part there. So the imaginary part of a bubble computed like that, with this prescription here, is 0. Now, the optical theorem told you that this should be equal to some square of a process, and that should be 0. But remember that there was a sum over intermediate states. There was a sum. So the only thing you have to do now to get unitarity is to project away those states. So we had a sum where there was intermediate states with 1s, physical particles, and -1s, ghosts. But that's the Feynman prescription. With the Fakeon prescription, you get intermediate states with 1s, those are the physical particles, or 0, those are the Fakeons. So the solution is you just have to project the space, the Fock space W, onto the subspace of physical states. There unitarity holds. And this works to all orders. You can find it in this paper. general proofs. And okay, now I want to discuss about some physical implications of this, because the key here is encoded in two words. One is the prescription for a new kind of particle, let's say a fake particle, because it disappears from the set of asymptotic states, but it is still around. We will see what it produces physically. And the other key word is the projection. The projection is very, very important, otherwise you do not have unitarity. So let me tell you what happens if you want to use these ideas for quantum gravity. You can, for example, start from this renormalizable theory. The matter sector is here, but you have to quantize the spin to massive pole in this new way. More explicitly, let me do it more explicitly, because here there are complicated propagators. You can write with extra fields an action that has no higher derivatives. So you have three fields. You have the metric, a massive spin 2, and a scalar. The metric has the usual Hilbert action. The scalar field has an action that is nice, okay, and the spin 2 field has a complicated action, but if you work it out, you will find that it is just a Pauli field, covariantized Pauli field with a non-minimal coupling, many vertices, but the wrong sign in front. So this is what you normally would quantize as a ghost, but again, this is a ghost only after you endow it with a given prescription, which is the Feynman prescription. Before that, you cannot claim it is a ghost. And if you quantize it in this different way, it can be given sense of, because it is a fakeon. What about phi? Phi can be quantized in both ways. So I stress this because since this is very, very general, it does not apply only to Levy models. It doesn't need higher derivatives. You can turn anything into a fakeon. The Higgs field, as far as we know today, I analyze the data, but I will talk to people here because here they are the experts on that. We cannot exclude that Higgs field is a fake. Even if the sign in front of the propagator is plus, it doesn't matter. If I quantize it this way, it will give different physical results, and it will never be observable. Now, there are many consequences and predictions you can work out to one loop. We did many things, including we calculated also, because there was, I mentioned Marco Piva, who is now a postdoc in the States. Many of the calculations are in papers done with him. I cannot go through them. Let me tell you something upsetting about the classical limit. The point is that I started from a classical action, which is like this, and you can call it classical action. This is not the classical action at all. This is unprojected. 10 minutes, very, very good. This is unprojected. There is a lot of work to do here. It contains something redundant, something that has to be thrown away, and that's not trivial at all. So, for example, if chi is a fakeon, it has to be projected away. If chi and phi are both fakeons, they have to be projected away, even in the classical limit. What is the classical limit then? Work out the field equations of that action. Here they are. The equation for the metric, phi, and chi. What you have to do is solve, for example, this equation with what initial conditions? You have no freedom. This is not a physical scalar. You have no freedom to choose the initial conditions. This has to be solved with the Fakeon prescription, actually the classical limit with the Fakeon prescription. Here you don't need at the classical level to deform integration contours, to squeeze regions. It's much simpler, but still it's non-trivial. And in this particular case, and only in this particular case, I stress it again, you can take this distribution as you see it, and that is the principal value. Only the tree-level limit, I stress it again, because if you use that in loops without the rules I told you, you generate a lot of problems. Then you insert the solution with this prescription into the other equations of the action, and you find the correct classical limit. But the final action is non-local, violates micro-causality, we'll see in a moment, and it's not even the end of the story here, because this is just formal a little bit. Now I tell you what happens concretely. Let me do an explicit example to warm up. Non-relativistic mechanics with a higher derivative term and external force. This is the unprojected equation. What do you do to make the fakeon disappear? You take this part, you invert it with the fakeon prescription, and you will find, instead of f equal ma equals to some average of f with a wiggling function that picks up past and future for very small times given by this. But that's it. That's simple just because this is an external force, and this is a very simple theory. It's much more complicated in general, so let me give you an example with the Friedman-Robertson-Walker metric. You can find the details in a paper that appeared today in the archive, GRQC. You can choose an ansatz for chi mu nu, the spin 2, to throw it away because it doesn't, as it shouldn't matter in the Friedman-Robertson-Walker scenario. So basically it's like having this. Technical details you can find elsewhere. If you work out the field equations unprojected, notice that they can be written in this nice form. Don't know if anybody ever noticed this, but if you combine the two equations in a certain way, you factorize the fourth derivative operators into these products of two derivative operators. That's very important. And the two derivative operators are here. Those are, let's say, the fakeons. And if you want to project them away, take this one, invert it, put it on the other side with the fakeon prescription. Take this one and do the same. And even for phi, you get a factorization like that. So formally, you get these projected equations the same as usual, but on the right-hand side, instead of having rho and p, you have averages. And these averages know about A itself, because sigma is a complicated operator. Now, you can say, okay, finally, you told us about the projected equations. No, this is not the end. Now I tell you something upsetting that happens. This is the end only if you give me rho and p as external fields, then I can tell you these are the projected equations. But whenever you have to solve, as you usually have to solve these equations self-consistently for rho, p, and k, this is far from over. The projection will continue because there is a lot of issues here, and in the end you will see that the classical limit carries many features of the quantum theory it comes from, and since the quantum field theory is formulated only perturbatively, my Fakeon prescription is formulated only perturbative, this classicization of the quantum theory is formulated only perturbatively, and so the classical field equations that you will obtain will contain asymptotic series just to write the equations, not only to find the solutions. You will have an infinite thing when you try to disentangle this self-consistently, an infinite tower of terms. But in some particular cases, even in quantum field theory, you can get to exact results. You have exact results from the perturbative expansions. These are anomalies, which are one loop exact. There is the renormalization group flow. There are many examples where you can resum, for example, the bubble diagrams, and you find the width and the lifetimes. There are some special cases where you can handle this projection exactly. For example, I mentioned this very important case, which is the superposition of radiation and the cosmological constant, the radiation and the vacuum energy. Instead, if you try and solve these for a general equation of state, P equal W rho, or dust, the simplest case, for example, you will find asymptotic series and all sorts of issues like that. Check my paper of today if you're interested. So, conclusions. Quantum field theory of particles and fakeons often offers new opportunities to high energy physics and quantum gravity. Fakeons do not belong to the asymptotic states. They cannot be observed directly, but they can be observed indirectly because they change the values of the imaginary parts of loop diagrams above certain thresholds. So, for example, what if the Higgs is a fake? How should we prove it or disprove it? Well, we have to make very precise measurements because those imaginary parts get into the cross sections and the plots that you measure here, but only above the threshold. For example, LEP2 stopped at 210.9 GeV, and the threshold for a bubble with Higgs and Z boson is slightly above 216, the sum of the mass of the Higgs and the mass of the Z boson. So they missed it. I'm not sure they would have been precise enough, but of course LHC is much less precise. There is something to think about here, but it's a possibility. It's a possibility. I can exclude, for example, instead, by the same argument, I can exclude already that Z is a fakeon. It's not. W's, they are not. I can exclude for most particles just from this analysis, but you know the Higgs is a little bit peculiar, so who knows. Fakeons allow us to quantize gravity. With you can have renormalization and unitarity. The violation of causality occurs at energies larger than their masses, the masses of the Fakeons. What is the mass of chi mu nu? What is the mass of phi? I don't have a prediction. They are free parameters, but I could place them in around 10 to the 12 GeV from various arguments. And the classical limit also carries many features of the perturbative expansion, including the fact that you will have no exact classical field equations. You have to deal with this. So when you want to probe quantum gravity, when these effects are important, you will have many troubles, even if you want to stick to the classical limit. So last comment. Let's see, I have only 2 minutes. What about scale invariance? What is the ultraviolet limit of this theory? Is it nice? I can tell you from the beta functions, it is not asymptotically free. Is it asymptotically safe? I don't know, maybe it could be asymptotically safe. Other indications suggest that it might be a little bit out of control because there is a Pauli fields action type, and you know that those kind of things have not nice ultraviolet behaviors, but they might be, everything might conspire to give something meaningful. However, I want to convey a message in the end, which is why I like the theory that is not under control in the ultraviolet, because in what I found in my research, not only in this case, is a pattern that's quite clear to me, maybe not to many other people who are mostly focused in searching for symmetries and beauty and mathematical elegance. What I see is instead something totally different, which I call radial irreversibility. Namely, you have determinism at our scales. Then when you go to the atomic distances, you have quantum uncertainty, and then now maybe you will have to deal with a violation of causality. That's a pattern that I most favor, because it tells you that basically you have freedom at small distances and lack of freedom at large distances. So in some sense the universe is not radial reversible, so it's uninside-outable. So that's the message that I want to leave you with. Thank you.
You,
you said that the Higgs could be a fakeon, the W and Z cannot. How is that compatible with SU2, which can rotate the components, longitudinal components of W and Z into the...
SU2 is broken, yes.
Well, but you know, what if I go to the unbroken phase?
That is, if you go to the unbroken phase, then you run into some troubles, because but there is a singularity going from one to the other. So,
well, it seems to rule out your.
You can jump.
Assumption that one Higgs has 4 real components.
Yeah.
You're saying one of them is a fakeon and the other 3 are not.
But the one that is a fakeon is invariant. It's SU2 invariant. It's the absolute value.
The classical law of the invariance is there, right?
Yeah.
It's just a quantization prescription.
Yes.
How can you state that when that's just invariant?
The three non-SU2 invariant components of the fakeon of the Higgs are gone. I'm not quantizing those as fakeons. But to reach to that one component, yes, it's singular. But at low energies, it's what works.
I'm a functional integral man. So quantum field theories for me are defined by functional integrals because that's non-perturbative and the standard model is perfectly defined in this way. Now, the standard model, you go up, let's say, to 10 to the 14 GeV, whatever you want, then everything is universal. Everything is predictable in terms of a few renormalizable couplings. And these predictions are precise up to effects of 10 to the power minus 28 or something like that at least. How can there be any freedom in the behavior of the Higgs boson mass? I mean, you're really contradicting the basic insights of universality, that we can predict everything in terms of a few renormalizable couplings and that these predictions are unique. And if I formulate it as a functional integral, this is really what comes out.
What I'm talking about is not going to change that, because a thing that allows me to conclude that this is a solution of many problems that there were before in quantum gravity is precisely that I separate the real part and the imaginary part. Normally, you had to choose. Quantum gravity, either it is renormalizable and then you break unitarity, or it is unitary non-renormalizable then. Why? The tie between the two is the prescription, I epsilon. With a different prescription, I make them travel on different tracks. The entire renormalization group is real, is the real part. It will be the same.
It makes statements about by analytic continuation about the full imaginary part. I mean, it's a predictive theory.
Oh, yeah.
Theory.
This is
predictions.
But those predictions are the same if I change the quantization prescription for the Higgs up to corrections that require very precise measurements. I think they are reachable in our lifetime, actually.
I told you it's 10 to minus 28 relative if you go to 10 to 14 GeV.
I claim
so
that those are
something bigger.
I claim that those are the invariant in respect to this change.
In terms of practical terms, so if you indeed assume that the Higgs is a Fakeon field, so what is your prediction? So the on-shell amplitudes which we measure are consistent with the SAM, and off-shell amplitudes one peak, or what is exact prediction?
What changes in the prediction?
Yeah, so the off-shell amplitudes are not fine, are deviate from the SAM.
So, for example, let me take this picture for the Z peak, okay? You have the peak for Z, where you saw Z. Then you go, so this is Z boson. You can have many interesting things, and also triangle diagrams and box diagrams. Let me focus on the self-energies. You can have, for example, a loop with W's here. W, W. You will see in the peak that there is something here. That's where the imaginary part coming from this bubble starts contributing, and many other things. So it's very, very complicated because there are many effects. It's not as simple as that. But you will see that at 180 something GeV, you will have something like that. Check that is the sum of those masses, because that's the imaginary part and the threshold. Now, there was a diagram where you could have seen if the Higgs were a Fakeon or not, which is this one. But at 209 GeV, LEP stopped And the threshold for the imaginary part here is mh plus mz, which is 216. If you go to 216, 230, and you are precise enough, you should see something like that, or something missing, because this is due to that, and you should not see something similar if it is a frequency.
What happens in the H threshold, the resonance? We see that resonance.
Oh yeah,
At
that's
125.
yeah, that is not changed. That's precisely the reason why you have a fake particle. Maybe this I should explain. This the fake particle is a mediator of interactions that cannot be observed by itself, but it mediates. It still mediates. What you observe there, sorry. What you observe in the peak of the Higgs is this. It's something giving the Higgs and decaying to something else. I can show you that in my theory that is unchanged. So because you do not observe the Higgs, you observe the...
Okay, so the optional amplitudes and the cross-sections are not changed.
Unless you go to one loop corrections above certain threshold, even that is changed a little bit.
I have a quick causality question. You mentioned electrodynamics with a third order derivative equation. Now, that equation is derived using the Leonard-Bishop potentials and radiation reaction. And that's completely causal. So the third order equation is a causal equation.
But
what people do with it, they mutilate it to make it non-causal. But nobody, you shouldn't be allowed to do that. If you've got something causal, you have to stay with it causal. You're not free to mutilate it.
Why?
Because you've got a causal equation. You
Why?
have no mechanism for acausality. You're inventing it. You're in QED, and QED is a causal theory. So how can
But
you...
that is an effective. Yes, that is, however, an effective. I don't doubt that QED is a causal theory. Yes, but that is an effective description. So when you have runaway solutions, you can trade them for a violation of microcausality, but then you find that the violation of microcausality is anyway covered by quantum effects. So at the effective level, both are equivalent because you cannot distinguish them.
But the total energy is conserved, and the runaway solution is powered by a renormalization of the mass. It's just a transfer of energy. It's a self-energy problem for the mass of the particle that you're studying. But the total energy is constant. The Hamiltonian is constant. It's a constant of the motion. So it can't grow at late times, even if it has a solution, even if one of the modes does. The whole thing has to be time independent.
I'm just saying that at that level, you cannot experimentally tell the difference.
Okay, so it seems that there's no more comments or questions on this.